Hello, myself Dr. Sridhar, working as Assistant Professor of Mathematics, Government First Aid College, Gokak. So today I am taking the topic Proof of Fermat's Theorem in number theory. So Fermat's theorem, it states that if P is a prime number and n is a positive integer and relatively prime to P, then n raised to P minus 1 is congruent to 1 mod P. So this is the statement of Fermat's theorem. So now we prove the theorem. Proof. So what we do is, first we prove that P divides a plus b whole raised to P minus a raised to P minus b raised to P. So that is what we do. We use the binomial theorem. So a plus b whole raised to P, it can be written as, by binomial theorem, it is equal to a raised to P plus PC1 into a raised to P minus 1 into B. And similarly, second term, PC2 into a raised to P minus 2 into B square. Next, third, PC3 a raised to P minus 3 B cube, and so on. The last term is, it is B raised to P. Now this term becomes same. A plus B whole raised to P is equal to, now what we do is write the first term as it is, and next take the last term, that is B raised to P, and write here A raised to P plus B raised to P, and write the remaining terms. PC1 a raised to P minus 1 into B plus PC2 a raised to P minus 2 B square, okay, and so on. And similarly, this can be written as a raised to P plus B raised to P plus, now instead of writing all these terms, so write the summation form. That is, here we take this whole as summation from r is equal to 1 to P minus R PCR into a raised to P minus R into BR. Okay, so this is the summation form. Now what we do, bring these two terms to here, that is, I write here a plus b whole raised to P, then bring these two terms here, minus a raised to P minus b raised to P, okay, is equal to summation from r is equal to 1 to P minus R, then here PCR a raised to P minus R, and the next term is BR, B to the power R, okay. So that is you can write this one as a plus b whole raised to P, take minus common, so a raised to P plus b raised to P is equal to, now write this term as it is, r is equal to 1 to P minus R, okay, PCR a raised to p minus r b r. Okay. So now now what I do, now we know that PCR is equal to, by using permutation formula, so PCR can be written as p factorial divided by p minus r factorial into r factorial. Okay. So now as we know that p factorial is equal to what? P into p minus 1 into p minus 2 and so on 3 to 1. That means p factorial is divisible by p. Okay, that means p factorial is divisible by p. So as p factorial is divisible by p, so therefore when this p factorial is divisible by p, then this whole term is also divisible by p. So when this whole term is divisible by p, then PCR is automatically divisible by p, because this PCR is equal to this term. Okay? So therefore p is divisible by p, so therefore PCR is also divisible by p. So now by divisibility property, therefore by divisibility property, what we have, if a divides b, okay, if a divides b, then b can be written as, if a divides b, then b can be written as, there exists a number k such that b is equal to a into k. So therefore PCR is also divisible by p. So therefore by divisibility property, there exists a number k such that PCR is equal to k into p. PCR is equal to k into p, because p divides PCR. So now replace this PCR by kp in this equation. So now let us call this equation as 1. This equation as 1. Now substituting PCR is equal to kp in 1. So then we get. So now substituting PCR is equal to kp in equation 1. Then we get a plus b whole raised to p minus a raised to p plus p raised to p is equal to, now this summation sign as it is, r is equal to 1 to p minus r, and then this PCR is replaced by k into p into a raised to p minus r into b raised to r. Okay, or again this is same as a plus b whole raised to p, a raised to p plus p raised to p is equal to, take p common, so then it gives r is equal to 1 to p minus r, a raised to k into a raised to p minus r into b raised to r. So this implies that this is divisible by p, because it is a multiple of p, so this is divisible by p. So which implies when this is divisible by p, then this is also divisible by p, because both are equal. So this implies that a plus b whole raised minus p plus b raised to p is divisible by p. Okay, so this means P divides a plus b whole raised to p minus a raised to p plus b raised to p. Or in other words, we can write, we say that a plus b whole raised to p, okay, is congruent to a raised to p, is congruent to a plus b whole raised to p is congruent to a raised to p plus b raised to p mod p. Okay. So now, in the same way, we prove the theorem for 3 terms. Similarly, if there exist 3 numbers, say a, b, c. Similarly, so we write a plus b plus c whole raised to p is congruent to here a raised to p plus b raised to p plus c raised to p mod p. Okay. Similarly, if it contains n number of terms, okay, say a1, a2, a3 and so on up to an. So then we write similarly for n terms a1 plus a2 plus a3 and so on up to an whole raised to p is congruent to a1 raised to p plus a2 raised to p and so on up to an raised to p, okay, mod p. So now what I do, take a1 is equal to a2 is equal to a3 and so on up to is equal to an, all are equal to 1. Taking all are equal to 1. So then what it gives, 1 plus 1 plus 1 and so on up to n times whole raised to p is congruent to. Similarly here 1 raised to p plus 1 raised to p plus 1 raised to p and so on up to 1 raised to p. It is equal to mod p. So now here 1 plus 1 plus 1 up to n times, that means its value is n. Okay, its value is n, so it becomes n raised to p, then it is congruent to. Now again here 1 raised to p is nothing but 1 only, so 1 plus 1 plus 1 up to again n times, it is equal to n, and n mod p. So now this can be written as, this is n raised to p, this can be written as 1 into n raised to p. Okay, 1 into n raised to p, because 1 into anything is again the same thing. So 1 into n raised to p. So now again 1 is the same as n raised to 0 is also equal to 1. So therefore I write this as n raised to 0 into n raised to p is congruent to n mod p. So now this 0. Now this 0 is, I will write 0 as 1 minus 1. Okay, so that is n raised to, I will write this 0 as 1 minus 1 into n raised to p is congruent to n mod p. Now what I do, using a loss of indices, I write this as a raised to m plus n. A raised to m plus n can be written as a raised to m into a raised to n. So this is n raised to 1 into n raised to minus 1 into n raised to p is congruent to n mod p. Okay. So now I take this first term n raised to 1, that is n only. I write this n as n only. Then combine these two terms. So now this becomes n raised to minus 1, and here, sorry, it is n raised to p. It should be n raised to p. Now this combining these two will give n raised to p minus 1 is congruent to n mod p. N mod p. Okay, now dividing throughout by n. Okay, dividing throughout by n. Okay, dividing by n. Dividing throughout by n. So here n get cancelled and here n get cancelled. So that is n raised to p1. So we get n raised to p minus 1 is congruent to 1 mod p. 1 mod p. So this is the Fermat's theorem. Thank you.